Okay, the next section of the chapter, and the longest section of the chapter, is on the movement of a nerve impulse. And what I'm going to do is break this up into different screencasts and then tie it in at the end. So this is the opening, the overview of the nerve impulse, and I'm going to use a animation here to show yourself. Basically, the screencast is going to be taking a look at this, and then we'll discuss it on the other side. So let me bring it up. There it is. We're back. Press play. Come on. There you go. Come on.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge, and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, depolarizing the membrane so that the inside is negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
Okay, let's get out of this. We don't want to stop that. Cancel. Okay, this, just to give you a little bit of an overview, that is this. Unfortunately, it didn't work on when I tried this morning, so I had to look it up on the internet. This might be the best and closest one of these animations to the actual IB curriculum. Usually I have to say, oh, you don't have to know this, you don't have to know this. There is not a thing in this animation that you don't have to know for the nerve impulse. Everything, it basically covers everything. So if you have an issue with the notes, look at the notes, come back to the diet. Look at the notes, come back to this. I know it doesn't have the text on the bottom, but it does have things going on and going through. So we're going to break a lot of that up, but the diagrams there are super. So let's go over a couple of things here. So, and this that we already know. So this is what we know so far. And this is meant to be kind of like a flow diagram. So you receive a stimuli. Stimuli is transferred to a receptor, which is generally a sense organ, skin, eyes, ears. Okay, sense organs create an impulse, take that impulse to the central nervous system, spinal cord, and brain by sensory neurons. Within the central nervous system itself, relay or interneurons transfer the impulse in the, again, you find only relay neurons in the central nervous system itself. So basically, they hand off the impulse to the response, which the response is taken back to the muscle or the gland by motor neurons through effectors. Okay, so two effectors, not through, two effectors. All right, and there you see it. Now you'll notice here you have it coming in. So you have two complete neurons here. They're not necessarily, the one thing we notice that this is not a myelinated neuron. However, you've got a dendrite to cell body to axon, okay? And you'll notice, here's another thing that we're going to need to discuss here, that the neurons are not connected to each other. As you go through, there's no connection point to it, all right? Hensing the word synapse. Yet there has to be a connection point to it because the impulse has to jump from one neuron to the next neuron. And so we need to speak about how that happens. It's called a synaptic transfer. And you need a chemical called a neurotransmitter in order to do that. All right. So here's the diagram that I'm going to work off of this one here, but the animation that you have is